Hi everyone and welcome to this tutorial on RSPt calculations. In our previous video we set up the crystal structure, and in this video I will show you how to set up the calculation. There are a few more things which have to be done. Apart from creating the crystal structure, we also need to generate the starting atomic density, we'll need to generate the keypoint mesh and adjust other settings. So let's go through these steps one by one. Here we copy the file which we created last time, which is a crystal structure of cobalt to iron aluminum. Now what we have to do is to create a directory called sim, and we put the simt.inp file in there, like so, and we run simt-all once again. Okay, we get the files which we are familiar with, but if we go to the directory up, we will see that a few more directories have been created. Coming back to the list of tasks which we have to do, first we have to generate the atomic densities, and this we do in the directory called atom. We can go there. And now you can see here there are several files corresponding to different elements what you have in your unit cell. So this is aluminum, this is iron, and this is cobalt. So let's go and check how this file looks like. So it contains information about the atom with its atomic number, and then it has a list of orbitals, 12 orbitals in this list. So the meaning of these columns is the following. The first one is the principal quantum number, second is relativistic quantum number, then we have occupation, spin polarization, and the mode. So the mode can be either relativistic, which R stands for, or it can be S, scalar relativistic. So the first line represents the 1s state of iron. We can see that it's doubly occupied and it will be treated in relativistic mode. This is done so for all the orbitals which belong to the core. For example, here we can see 2s and 2p states, but now 2p states are split. You see there are 6 electrons in total, but they're split into double degenerate and 4 times degenerate manifolds, which correspond to J1/2 and J3/2. But now when we come to the 3d orbitals, so L is equal to 2, they're split in a different way. Here we decide to use scalar relativistic mode, and this is so because we want the states to be spin polarized, meaning that we assume that the spin is a good quantum number, and instead of occupying orbitals according to their J quantum number, we use spin. We put 5 electrons in spin up channel and 2 electrons in spin down channel. It will create an imbalance of 3 electrons, and that's exactly what we want. If we don't split the states, then we will just end up in the non-magnetic state, which is also a local minimum. So all what we have to do now is to generate the density, and we just have to run make. So if that doesn't work for you for any reason, make sure that you have a variable called RSPt home in your environment. We got different out files which we don't actually have to look into. You can see some information here on the screen. You see that the program basically was solving Schrödinger equation for each atom separately, assuming that they are isolated. Great. We don't have to do anything else. We just exit this directory. And now we can see that we get a new file called atom dense. So this is a necessary file to start the calculation. Coming back to our list, next we have to generate the keypoint mesh. And in order to do this, we have to go to the directory called BZ, standing for Brilliant Zone. And there are two files. I would recommend to have a look into both of them. So cube.doc contains important information when it comes to the choice of divisions in the Brillouin zone. So here it writes suggested dimensions, and I strongly recommend you to follow this. So what it says here is that the dimensions have to be with ratios 1 to 1 to 1. We have a cubic system, and in order to have a uniform mesh, we have to make divisions equal in all three directions. And in the second file, it contains the Bravais lattice and also this M matrix. So this M matrix is used in addition to Bravais lattice matrix to generate the K mesh. And here you see that it basically also follows the FCC structure. It doubles each Bravais vector. It's done so that the mesh is more uniform, and there are automatic algorithms inside taking care of it. But in certain symmetries, for certain lattices, you get some obscure results sometimes. So I would strongly recommend you to check that this matrix M makes sense, because sometimes you start getting weird elements in this matrix. And if it's the case, I recommend you to restore this matrix to unity, because this is the safest choice. Because if you use unitary M matrix, what the code will do is to use directly this Bravais lattice, and it will make divisions just along these three Bravais vectors. But for cubic systems, it works just fine. So we can use this M matrix, and we can use the dimensions which are suggested in the cube.doc file. Okay, let's generate the K-mesh. For this, we use the program called cube. Now we have to enter the group name, and by default it just uses the simconf file, which was generated by simt program which we ran before. So we can just hit enter here. And now we are entering the dimensions. So let's take 16, 16, 16, and here we add the shift. So if we want to include the gamma point, we don't apply any shift, and if we don't want to include gamma point, we use some shift. So here we can shift the origin by 1/2, 1/2, 1/2, like so. And here we just have to hit enter a couple of times, and as a result we got several files, but the only one which we will need is cube.k.16, and it contains the K-mesh. This is the total number of keypoints generated for this mesh, and this is the number of irreducible keypoints. So we have a K-mesh, but we can have several K-meshes. So we have to make sure that the calculation uses the correct one, and for this we have to link it. So we use this program called link_RSPts, and we have to specify the file, which is the postfix of this file, cube.k, and in our case it's 16. So we come to the final step where we have to adjust so-called other settings. So this is the list of files which we will modify in the DTA directory. So we go to DTA. There are plenty of files, but only few of them have to be modified. So we need to adjust the way we integrate the occupations. This is done in this file. So let's go and modify it immediately. So here 1 stands for tetrahedron method, but we will use Fermi smearing because this is something what we have to use when we run DMFT. And now, since we use Fermi smearing, we have to set effective temperature, or how much we smear the Fermi Dirac statistics. And this is controlled here. This is exactly the width of a Fermi-Dirac smearing. Let me just use 2.5 millirydberg, which roughly corresponds to 400 Kelvin. And here, this is a bit technical. It's a threshold for defining which states are completely occupied and which are not. So let us just set this parameter to 64, which is a safe choice for this temperature. The next file which we have to modify is the tail energies. The way RSPt works is that it uses atomic-like orbitals. Here we have one parameter which is called tail energy, and tail energy specifies the extent of these basis wave functions. If this number is positive, then the wave function will be oscillating at large distances, and if it's negative, it will attenuate. And the more negative this number, the faster it attenuates as a function of the distance away from the atom. The common wisdom here is that the first two tails have to be as different as possible, and the third one is somewhere in between. I prefer the safest choice, set all three tails to be negative, and it's because I want to make sure that the basis functions are localized. Sometimes it's unavoidable, because if you work with systems which are confined in certain dimension, like slabs or wires, you have to make sure that the basis set is localized. Otherwise, it would be very hard to converge. Now we will go and modify the element file. And since we have three different elements, we will have in principle 3 files to modify. So let's start with aluminum. Here we have quite some useful information, such as Muffington radius and the number of radial points for integration. We have core states listed here, and most important is the description of our valence electrons. So here we have 8 entries in our basis set. The first 3 correspond to aluminum S states. So the first column corresponds to L quantum number. So this is S, P, and some D states. The second column corresponds to the energy set. And in RSPt, you can have several of those. In our case, all the states belong to one energy set. You need several energy sets if you have some valence states and semi-core states. And finally, we have this column which contains the index of the kinetic energy tail. So this means that the S states of aluminum will be described by all 3 basis functions, with tail 1, tail 2, and tail 3. Same stands for P states of aluminum, while the D states will be described by first and second tail only. And this is something common. You will see that for certain elements were only 2 tails which are used, and that's why in the tail energies file we wanted these 2 basis functions to be as different as possible, because for certain states only those are used, and if the basis functions are too similar, then you can run into linear dependencies and you won't be able to diagonalize the Hamiltonian. And finally, in the end of this file, we have a list of orbitals once again, but here we have choices of their linearization energies. Now these numbers encode principal quantum numbers corresponding to these states. So here we had S, P, and D states, and here they're listed in rows, meaning that we have 3 S, 3 P, and 3 D states. And we have the same for spin down channel, and it's just duplicated for the energy set 2, which is not used for this element at all. And 0 here is a special choice of linearization energy. In case of aluminum, the only thing we might need to modify is the muffin tin radius, and in order to do it, we have to adjust this number. But by default, what's used is actually the volume and not the radius. To make sure that the code is using the radius, we have to add one more slash here and remove it from here. Now we can modify the muffin tin radius, and we can put it strictly to 2 bore. I'm sure the default radius was fine, and this is just to show you how it's done. Good. Then we go to iron element file, and here it gets a bit more interesting. First of all, we see many more basis functions. So we have S, P, D, and again S and P states. And it is so because these states correspond to free S and free P states. They correspond to the second energy set. So we have to look here, what are the principal quantum numbers? And indeed, it's 3s and 3p. Good. So by default, these states are treated as valence, although they are lying somewhere at 50 electron volts below Fermi level. We can safely put them in a core in the case of iron, and in a separate video I will show you how to do it. But for the moment, let's just use the default setup. For this element, since we have 4s and 3s states at the same time, it might create problems for our code, and we will see what kind of problems we can have. Okay, but for the moment we leave this file intact. Let's again set muffin tin radius to 2.22, just to have a bit more beautiful number. Okay, and finally we go to cobalt. Again, we have 4s, 4p, 3d states in the valence, and 3s and 3p states in the semicore. So let's again just modify the muffin tin radius, and we put it to 2.23. Okay, next we can have a look at the Fourier grid file. And these numbers you will have to modify if you have a system where you have relatively small muffin tin radii, or if you have a huge vacuum and you have to make finer grid to make proper integration. So we can finally look at the header, and it contains some important information. So L max, so this is the maximum L in the decomposition of a potential. Default is 8, and it's pretty good. Number of types, so number of crystallographically inequivalent atoms. In our case, it's 3. Number of valence electrons, choice of exchange correlation functional, the mixing, and a few more parameters, whether a calculation is fully relativistic, false in our case, and whether it's spin polarized, true. Let's maybe decrease the mixing a little bit, and the default exchange correlation functional is AM05, but let's take something simpler and more common, such as one of LDA functionals. Okay, now from all these files we have to construct one single input file which will control the calculation. So before we do that, we copy the length scale to the directory above. We go here and we type make data. And indeed, you see we created a new file called data. If we open it, it contains all the information about the calculation. It has quite strict format, and it's not quite easy to create it from scratch on your own, but make data just created it for you. Now, if you want to change some small parameter, you can directly modify the data file. Otherwise, you can go to, for example, DTA element 13. Now you suddenly decide, okay, let me modify the muffin tin radius a little bit. I put it at 2.02. And now I have to recreate the data. So I run make data once again. And you see this line was updated to this one. And in the next video, I will show you how to check your calculation and troubleshoot it. But until then, enjoy RSPt.